and it actually show whatever it is. There's a lot of cool features about it. It just all right, one go. Yes?
How much does it matter, the distance between the two particles?
It does matter because if you look, it changes the shape of how flexy those are, right?
So like there's a difference between
Yeah.
the two. Okay.
You have to bend the lines much more sharply so they're closer together.
Got it.
Max 2 has 2 positives.
But 2 has 2
I know,
positives,
yeah,
that's a bigger difference.
Yeah.
But like I was just distance-wise.
But yes, distance-wise it's going to matter because you're going to become less dense. The lines become less dense, right? Which makes sense. Electric field should be less, right? Mm-hmm. So I've got, whoop, you should have something that looks like that. Okay, so it's coming out of this one. So the positive's got 4 coming out of it. The negatives got to have 4 coming into it because it's the same size charge, right? Mm-hmm. And then we just curve our lines. That's terrible. I just ran out of space. That's why it looked that bad. And the last 2 lines stay. Right? Got it? Got it?
Yeah.
Okay, try the next one. No, maybe ready for the next topic.
The lines just connect to the nearest one they can.
Yes. So try 4. 4's got some weirdness to it. Maybe we should do, well, we can do 5. We're going to do 2 right now, yes. This 2 is weird enough. We can do it. I'm going to make somebody do it with me, too. Welderman, you got it?
I think so.
All right. Hold on, let me put this in here. Okay, so I've got 4 positive and 4 positive right next to it.
Yep.
All right, so what's my rules? Let's go through them one at a time and do them the way we're supposed to, which is?
Right. So since it's positive, we're going to have arrows going out.
Going out. How much did you choose to put out?
4.
4.
Yeah.
Again, that is completely flexible. Now, they asked the right question earlier. You said, well, does it have to be? Now, did you put them at angles, which would be clever, or did you put them like I just did?
I've done like you just did.
All right, good. By the way, you can make yourself life better by having go at angles like this. Then it's really easy to draw your curves going out. That's the way almost every textbook does it. They don't want to deal with what we're about to do because it's not pleasant, but whatever. We got this. I've got this, 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 and this. So that's my first rule.
Mm-hmm.
Second rule.
Well, since they're both positive, they don't really like each other.
So there's no connecting at all. You cannot connect these. It's probably something to one place. Okay, they've got a key, so they can't be a student. At least I don't think it can be.
So much fun with biology students.
Okay, so next up, so that doesn't connect. Next, what's the next thing?
We draw lines.
The lines don't like each other, right? So we're going to try to steer them so they don't like each other.
Yes.
So obviously in the middle here we've got a problem. Now I don't care if this one goes up or this one goes down, right?
Oh, okay.
Whichever way you do, it can't matter, right?
Yeah.
So which way do you want to go? Which way do you go?
So I did the left as up in the middle.
Okay, so you went up like that.
Yep.
And this one goes down like that.
Uh-huh.
Which implies right in the middle, there's no lines, right? Right in the middle, there'd be no electric field, right? Because equal pushing both ways. Positive test charge would go nowhere. But if you kick it either way, what happens? It's going to take off, right? It's going to really get out of there in a hurry, right? Because the lines are very dense. Electric field is high here, right? Okay, from there, what'd you do?
The bottom one on the left, I just curved it to the left.
It should be curved like this to avoid this line here, which is, oops, that's too much lines. Should be going almost straight up and down, right?
Yeah.
This one should be that way. This one should be that way. This one's going to curve that way to get away from the other ones. Should be more curved than that. This is going to curve that way. This is going to curve over here.
Mm-hmm.
Great.
So what do you do about the end points? Because in the other drawing, when they went out straight, they were actually connected.
But that's not a real thing. They're not actually connected. So yes, we don't worry about it. Doesn't bother us at all. And to be fair, if we'd done the tilty thing, if I'd done the 4 plus like this, 4 plus like this, which is the way the textbooks would show you to do this. Again, how would you know until you've done a bunch of these and gone, well, that makes sense. I want to do it that way. Right? You curve that one, you curve that one there, you curve this. This one's going to curve something like that. This one's going to curve something like that. This one's curving down like this. It's curving like this. It's curving like that. This one's curving like this. Again, dead space in the middle. Density of lines. If you get closer, it's going to pop out of there. Okay. And so these don't have to connect. Okay. Good. All right. I'd like to do one more before I make you do this for homework. So try number. Want to do 4?
Yeah.
Let's do 4.
Yeah.
4 looks like fun. By moving all the little piece of paper around, the electric field is equal to V over D for what situation? Natalie.
The electric field.
Electric field is equal to V over D in one specific, very narrow situation.
See?
2 parallel plates, right? So if 2 parallel plates, and I'm going to get spoiler alert for that worksheet you're about to do. Okay? If this is positive, and that's negative, the flux lines would go out from here, equally spaced, and into here, right? So electric field lines would look something like whoop, 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 whoop. Now, the ones on the ends don't like these, right? They're trying to repel. So the ones on the ends would slightly bow out, as they could, right? But all the way through the middle, those are straight lines. And they're equally spaced. What does that tell me, Natalie?
It is a uniform electric.
Uniform electric fields, which means the electric field, which depending on the voltage and the distance, none of these 3 things are changing, so I can just use this cute little formula to solve for electric field between 2 parallel plates is, right? Mm-hmm.
Wait, do those connect around?
Yeah, if they go off into space, they would do this like this, and then like this, so they connect over here somewhere. And then this one here, we connect way, way.
That's alright.
They disregard the bell. How'd they screw that? Oh, that's just the normal bell system. They got the normal bells on again.
Please disregard that bell.
But people just went, oh, they're behind me, finally! Okay, so, all right. All right, so good. Okay, so electric field between these 2 plates is the same throughout, right? So I can use this formula. But what happens if I instead talk about the electric field? I got a charge and a positive charge here. I get a negative charge here. And I want to move the, I've got this little Boeing thing that we've been talking about all along, whatever it would be. If I'm moving the charged particle from here to, say, here, is my electric field changing? And it's changing with respect to distance, right?
Ooh.
So therefore, I have to do what instead? Integrate. So this whole front page was to justify what I'm about to say, which is we need to integrate the electric field with respect to distance, and I'm going to use R for distance because we can't use distance because that's bad. dd just bothers us. And that's equal to the voltage. So the electric field, the integral of the electric field with respect to distance equal to voltage, that big old space right here. All of that is to justify what I just wrote there.
Where?
This is on 11.2. There's gravitational potential energy, electric potential energy. It's got all this garbage up there. Just, that's it.
Okay.
So you usually don't do this, but you trust our calculus?
I think we've had better conversations on the calculus in and why you need to change things than we've had about potential energy and the gravitational potential energy. I remember your gravitational potential energy knowledge and your calculus knowledge, and I'm now leaning more this way.
So
That said, I think this is cleaner. I spent, this is a very nice way to derive that this formula. It takes 25 minutes and doesn't really, it gives you the same thing. I'm not sure it gives you a better understanding anyways. It's that idea of, gravitational, you're lifting rocks and dropping them on things. Did that last time. You guys weren't big fans. Here we are.
If Walker were here, he'd be concerned. So should
Okay.
I be concerned?
Nah.
Okay.
All right, number 1.
What's this?
So, That's interesting. Now that leads to a problem. Moving backwards leads to a problem. Electrical potential energy is invested in. Trying to think. Does that actually do me any favors? Now I got to back up a sec. Hold on, give me a second here and think about this. Because I thought I had a clever way around this, but now I'm thinking maybe I stepped into it and then got around it. Let's do it anyways. We can do this. Okay, so the potential energy invested in a 2 coulomb charge, a distance 10 meters from a 10 coulomb positive charge. Because how much energy does it take to make that happen? Okay. Huh. All right, let's start off with basics. What's the energy formula for electricity? What do you got, Colin? He's in the back of the room, isn't he? What do you got? Yes, sir.
E equals S squared R. Right?
No.
Power, not energy.
We haven't talked about power or circuits at all yet. Or resistors. Yes. What?
Is it VQ?
It's VQ, right? The voltage difference, the potential difference. With me? These are these moments where you get it, and then later on, or you don't get it, and you're like, I've never seen this before. I don't know what we're talking about this. This is that moment, which is why his mother's making a record. Whatever. VQ! Confused before. 2 more class periods not going to help. Okay. U equals VQ. Make sense? So.
Someone's gonna watch these.
So, what am I doing? Lost my train of thought. Okay, so U equals VQ. So, moving forward, I want to find the voltage. So there's 2 ways I can find the voltage. One of which is to do this fairly simple, straightforward. Not very straightforward. I've got a charge of 10 coulombs, right? And I'm going to move my test charge, my -2 coulombs, from where to where? To figure out how much potential energy you have. Well, where would it have the most potential energy?
Almost
In
touching.
between.
Well, it's way over here at infinity, right? You have an infinite amount. Where would it have the least?
In the middle.
Well, it's sitting here, right? So if I'm talking about how much potential energy I have, wouldn't it be if I take my -2 coulomb test charge and bring it out to this spot right here? Yeah. Wouldn't that be that would be the potential energy I have that I could get back?
Wait, back up.
Backing up.
You have the most potential energy at infinity?
At infinity, right? Because as I lift this thing, the force would be the least.
No, I disagree.
Okay.
Be infinity that way.
Why would it matter?
Because the 2.
No. This is, I'm taking this and I'm moving it around. I'm taking this particle and moving it around. Where would it have the most potential energy?
Okay, now I get it.
Over here,
I thought this-
and then the least right here. So it would logically we'd want to put it right next to it, right? To find the voltage, we just said that's the integral of the electric field dr, right? Well, all right, voltage is therefore equal to electric field. Well, electric field, what's electric field a single charge puts out? Crowd goes quiet
Not very good.
because we haven't spent enough time on that.
0. Shoot.
Wait, say that again?
Undefined.
Undefined.
Because your D is going to be 0.
Ooh, interesting. Okay, so let's not jump that far ahead. Let's think about it in terms of variables at the moment, and then we'll talk about why we can't do it. We're going to get to what you said. You're 2 steps ahead of us. Okay, so the electric field is equal to force per unit charge, right? And that's this charge that I'm moving around, right? So if I go electric field is equal to force, what's the force formula for 2 charges? KQQ over D squared over Q, right? One of these Q's is the same as that Q right there. So I want you to remember this because this is useful. It happens a lot. It's one of those things that you want to have in your bag of tricks. I'm going to use R instead of D because it's going to come up a lot. Okay, the electric field caused by a single charge is that around it. Okay, it is the charge's single charge, this constant 9 times 10 to the 9th, divided by the distance between them squared. That's all they need for force, not counting. It's weird.